everyone. Welcome to the Kistler webinar on multi-component force measurement for space applications, practical aspects. This is part 2, and I'm glad that you're joining us today to this very interesting webinar. My name is Pascal Erne, and I'm Business Development Manager for the Department Test and Measurement at Kistler. Please be aware that today's webinar is recorded. The recording will be shared with you after the webinar. Be aware that you are muted on purpose. If you have any questions, feel free to use the box on the right-hand side, the Q&A box, and post your questions there. After the presentation, we will answer the most interesting questions of the Q&A section and get back to you by email if we are not able to answer all these questions within the time. And now I'm very proud to introduce our today's presenter, Bill Zwolinski. Bill holds a master's degree in electrical engineering, specializing in signal processing and controls. Prior joining Kistler some 20 years ago, he has worked in the field of underwater acoustics and has been chief engineer for the Navy carrier landing system at Textron. Currently, Bill is Business Development Manager for Test and Measurement Applications at Kistler, and at the same time acts as an application engineer. With this enormous know-how in both the mechanical and the electrical world, he's heavily involved in solving our customers' measurement problems. And now we are ready to learn something new, Bill. I hand over to you, and the stage is yours.
Okay, thank you, Pascal. Okay, so just to go over the agenda today, we went through part 1 about 2-3 weeks ago. And if you missed the part 1, I encourage you to go to the YouTube link and feel free to listen to that if you'd like. So in this part 2 session, I'm going to have a brief review of a few slides of that, and then also go into some applications, and so we can see, how you apply some of the concepts we've reviewed already and how it basically works. So that's the plan anyway. So just some basic introductory slides right now. Basically stuff I covered in part 1 is the terminology PE and IEPE is piezoelectric and internal electronics piezoelectric. Basically are the two types of piezoelectric sensors that are commonly out there. The piezoelectric style is the one we're going to focus on in this session, but the IEPE is quite popular as well in terms of, I'll say you see that quite a bit in the acceleration field, for example. Vibration field would be one area where IEPE is used quite substantially because of the dynamic nature of that measurement. For the PE side and for force measurement, there's several advantages you have with regard to piezoelectric. One is there's no electronics inside the sensor, so that means that we have a signal conditioner external, and that gives us the ability to vary the range of the measuring chain. So you get multi-purpose use out of one sensor. You also get the ability to vary the low frequency and high frequency, because there's filtering options usually, and also be able to do quasi-static measurement. For example, preloading force sensors or very low frequency measurement would be also something that could very well be done with piezoelectric. So what we're going to do is focus on that technology anyway for this session with the space applications. One thing I covered last time was really, and one thing to remember, the frequency response of a piezoelectric sensor is that of a lightly damped second order system on the high end and a single pole high pass filter on the low end. So what that means basically is that you've got a relatively flat amplitude response with frequency, which is excellent, excellent to have. And there's actually some expressions you can apply, knowing that if you know the natural frequency, and it's fairly easy to test for natural frequency by a tap test, for example, and make it an FRF, you know that the approximation would be a 5% response would be the natural frequency over 5, the 10% natural frequency over 3, and obviously the 3 dB natural frequency over 2. So why is that important? Well, because we're always interested when we're making force platforms, force measurement platforms, is, hey, what does the test article need? Okay, so once you know what the test article needs, you can now look at the response of the design, how it works, the FEA, and apply some of these rules as a guide. Okay, obviously the detailed analysis is very much required in that, but these are guidelines. So this is something we'll probably come back to a few times during the discussion anyway. The other considerations for force dynamometers, and I do quite a bit of work with various entities around the country, and certainly there's a large interest to use dynamometers, force dynamometers, or make their own for custom applications at the company, or perhaps ask Kistler, to make a special one. But fundamentally, a force dynamometer is basically a combination or array of force sensors that basically are used to distribute the load, the non-axial load, across these sensors. And by virtue of the geometry of the sensors, you can utilize that to calculate resultant forces and moments, reaction forces and moments, if you will. And that's a pretty powerful technique. Obviously, with what I just said, the analog bandwidth considerations are important. Usually the charge amp is really the main piece that tells you what the upper and lower end maximums are, or minimums on the low end, maximums on the high end. The test article then defines what the required frequencies are and whatever that resolution might be in terms of noise profile. And then lastly, the force sensors or fixtures that are being made basically have to satisfy that. And a lot of times I get calls from various R&D groups, and we're always looking at ways of fitting these requirements based upon the type of sensor, the number of sensors, the fixture design, and so forth. But sometimes we have to resort to just using a wider amplitude tolerance. Okay, it might be the most practical aspect of a decision. Maybe you go from a 5% to a 10% tolerance to get the wider bandwidth. Various considerations were covered in the part 1. As I show here, I mean, everything from installation and mounting, alignment of sensors, the load-bearing surfaces, what types of materials are involved, what the tolerances are, flatness and parallelism, for example, would be required. Certainly, the selection of a sensor is very important. What you'll find in 3-component sensors is that as you go up in capacity, the actual stiffness increases quite substantially, and that gives a very powerful benefit to meeting, say, frequency response of a certain force platform. So that's something to take away. Obviously, even going sensors with higher capacity, because everything is rangeable, you have the rangeable ability with piezoelectric, you're not giving up so much anyway. It's something that definitely people consider in their fixture design. And then obviously mass loading was discussed as well, checkout and calibration, of the platform. And then what we're going to talk a little about today is a little about vacuum operation, some environmental considerations as well. So we covered quite a bit of topics anyway, and we'll continue to do more. What I didn't cover in the last session is I wanted to bring out the concept of moment calibration and K-factor correction. The reason why I want to cover it now is because we're talking quite a bit now on some of these applications on putting test articles on platforms, on force platforms. So you have some height, you have definitely some dimensions to deal with, and certainly what are the calibration factors. If you're interested in 6 degrees of freedom or 6 components, there are some other considerations. For example, if you had a test article with, I don't know, a couple feet or 0.2 of a meter type height, you might be interested in doing a custom or a specific moment calibration to determine these K factors. And basically, the concept here is when moments are applied through a lever arm, there's a non-ideal stiffness of the dynamometer causes uneven loading over the sensors of the dynamometer. And this results in a virtual increase of sensor distance. If you look at the closed form expressions up in the upper left-hand corner, you'll see that the A and B factors are basically separation, geometric separations of the sensor center to the center line of the dyno. So, what these K factors do is they help correct for these virtual differences by say, a non-ideal stiffness in our designs. And that requires basically a calibration that replicates exactly what your test scenario would be. The CG of your test article, for example, where that is located, and then you would apply forces with moment arms to determine these K factors. So it's something to just remember that it does exist and it is available on special requests. There's some dynamometers that actually come with a standard moment calibration as well. This is a typical certificate, and what I just show you here, on the moment calibration, there are moment correction factors here, which could be a value depending on your application. So I'm going to go into the new topics for part 2 session anyway. And what I wanted to cover a little bit was the noise, noise considerations. Obviously we talked last time of ground isolated measuring chains. This is a best practice in test and measurement, is to have ground isolated measuring chains. And what that means is that you have one common grounding point, and that avoids ground loops, which can give you unwanted noise. Obviously, avoiding strong electromagnetic fields with cabling is also important. Even though you may be using 360-degree shielded cables, if the electromagnetic interference is quite strong, it could still couple into cables. So it's very important to route cables smartly as best as possible, and to use shielded cables, of course. The battery-powered signal conditioners, obviously with AC power, is not a perfect process to convert to DC. So there are some harmonics and unwanted attributes of that. So to get rid of that altogether, a lot of times battery power is used, and it also reduces the noise floor as well. And bandwidth is directly proportional to RMS noise. So we'll go into that a little bit. There's some other topics that we'll cover, I'd say probably more aimed at the micro vibration applications, such as seismic inputs into your structure, the acoustic borne noise, HVAC inputs, external environmental factors which could couple in to your measurements. So basically noise, time and frequency domain, I think intuitively, I think we have most people understand how the time domain representation would work. You have a nice sine wave there on the left-hand side, you got additive noise, you come out with something that doesn't look quite like a sine wave. So what do you do about that? So you also have ways of looking at this in terms of the frequency domain as well. And basically that's what I show you over here, is the noise power spectral density gives you a representation of the noise power with frequency. So by specifying a frequency range, you can integrate that noise power spectral density and achieve or an estimate of the RMS noise. So that would be basically how this would be done. And that's what you see down there. Also, keep in mind that with FFT-based processing, FFTs can be thought of as a narrowband filtering, based upon the number of points in the FFT, the sample rates. So you could very well look at your system response in terms of noise on the basis of a bin width, and signal to noise ratio on a bin width, which could give you some advantages in identifying the harmonics that might be of interest, for example, in your measurement. This is an example of a DC power charge amp, or a battery powered charge amp. Basically what I show here is really the RMS noise on the upper hand column, and as I explained in part 1 session, very laboratory grade charge amps have usually on the low end like a 2 picocoulomb full scale range. So what does that mean? If you have a sensor that's say 4 picocoulombs per Newton, that would mean your full scale capability of the amp is a half a Newton. And that half a Newton would be equal to plus or minus 10 volts. So that's and then what you see here on the bottom is basically the dynamic range or the signal to noise ratio of certain selections, whether you have a 2 picocoulomb full scale range on up to 100, okay? And you can see at the 100 picocoulomb range, you have quite a bit of a dynamic range for sure. On the 2 picocoulomb side, you have on the order of 78, dB dynamic range, which is basically giving you quite a bit of visibility underneath that half a Newton example that I just showed you. What I show you here on the right hand side is basically a typical like 100 picocoulomb range setup where the green curve would be like a battery powered charge amp noise, and you can see that the 1/f noise is lower. And certainly if we showed this at a 2 picocoulomb full scale range, you would see a more prominent or dominant 1/f being quite a bit lower for the for that case. So, and you also see here that the harmonics of the AC power conversion process, because in this plot, although the data acquisition system, although the charge amp was powered by a battery, the data acquisition system was not. So the takeaway from this is to really get the best performance in terms of these unwanted harmonics of AC to DC power conversion is to power both the data acquisition and the charge amp with the battery power. And that's often done when you need the most or the best type of performance for your measurement. I would say it's not always done, but it is done when you need the best. There's other considerations with regard to electrical noise, and one is I mentioned in part one that this charge amplifiers have, some of them might have a summing calculator to derive these closed form expressions, the 6 components. Well, this summing calculator is basically an analog circuit with gain and scaling, that kind of thing, and sum and difference functions. So what that does is it does add some additional noise. So if you really wanted to get the lowest possible noise out of your charge amp measuring chain, you would power by a battery, both your data acquisition and charge amp, and you would take the charge out, the 8 amplifier outputs, and go right into the data acquisition with the 8 fundamental signals from the dynamometer, and then use software such as DynoWare or maybe your own custom software to compute the closed form expressions. This is definitely the lowest possible noise you can achieve when you're doing it by calculation. And then also I wanted to just mention the term harmonics. Obviously, in a lot of processes, a lot of things we deal with in our measurements have harmonics, and these are basically multiples of fundamental frequencies, where you might have a fundamental frequency of say 100 hertz, and then you'll have harmonics of that, integer multiples of that out in frequency. Well, a lot of times when you're talking to research engineers, there's a lot of it has to do with, well, what type of harmonics do you want to capture in your measurement? And that really folds into the definition of what the test article needs in terms of frequency response. So not only do you need to measure certain attributes of the test article, but there might be some harmonics that need to be captured. And it's not unusual to get requests of say 500 to 1,000 hertz in some applications where these harmonics want to be reviewed out to those levels. So it's definitely that would be definitely a higher frequency application for a force measurement platform. Also with vacuum measurements, there's certain reasons why you would do vacuum measurements. For cryocoolers, a lot of times they're being done because sound transmission in a vacuum isn't prominent. Obviously, it's not possible to travel. So this allows more precise evaluation of a cryocooler. Developing all the vibration control algorithms would obviously fold into that. With thrusters and propulsion test stands, the expansion of the gases would be overexpanded in a vacuum and would give you a higher thrust. So when you're testing thrust in a say a room environment, it's a much lower thrust than what you would see in a vacuum environment for some of these designs. So how do you achieve that? You have the vacuum chamber, which is pulling a high vacuum. You have low outgassing cables. You have a vacuum feed through. In this case, it would be multi-pin Fisher connector, a 9-pin Fisher connector. And then you would have the basically the cables and signal conditioning to enable you to set the range of the system as well as the perform the data acquisition. Obviously, with any vacuum type applications, you're always looking at low outgassing componentry. Okay, and a lot of times, companies, although might be told or guaranteed that they're low outgassing or have low outgassing materials, a lot of times there's a thermal bakeout, vacuum bakeout that's performed on site to ensure that the cables are not are going to outgas and perhaps contaminate some very sensitive, say, optics and so forth. There are guidelines, obviously. I mean, I referenced NASA guidelines for outgassing, which give, I mean, they're pretty comprehensive in terms of the types of materials and what is known to be good and not good and so forth. And obviously, there's test labs that actually can test to that degree as well. So in terms of vacuum applications, low outgassing cabling is and sensors are quite critical. Okay, there we go. Okay, what I wanted to talk a little about is the microvibration installation guidelines. So I mean, when you're doing an exported force and torque test, I mean, how do you, you've got a mechanism you want to evaluate. How do you go about that? Well, what I got here is a very simple illustration that shows a stone table, or a granite table, or optical bench on a pneumatic isolation system with an adapter plate that couples the dynamometer into the table. And then you have another adapter plate on the top that couples the test article to the dynamometer. And you also have some noise protection, so not to increase the environmental noise of the measurement. Adapter plates are quite critical, but I'll say first, the pneumatic isolation is there for mainly seismic inputs. The table and the stone table is there to minimize resonances or to put resonances of that table out beyond the resonance of interest of the test article. So that would be the main goal. There is for stone tables, there are, for granite tables, there are some general rules there, the 10% rule that says, all the fixturing on top of the table should be less than 10% of the mass of the granite table itself to get the best resonant characteristics of the table. Obviously, optical benches are a different type of system. You look at some manufacturers and they're talking about passive and active damping methodologies with these optical benches, and they're quite a sophisticated system where they're trying to sort of trade off on mass and to provide damping in some other sophisticated manners. So it's there's a lot of technology behind those types of tables for sure. The adapter plates, as I said, are usually thick and ground, flat and parallel. They usually have many mounting holes. The more fasteners, the better, is what I had said in the last session. So this dynamometer would have 5 mounting holes, and then you would at least mount around each hole into the granite block so to get the best frequency response. So how you mount the dynamometer and adapter plates will affect the overall frequency response. The top adapter plate usually comes in to be an aluminum plate, what we recommend. A lot of times we're not looking at a lot of heavy bending moments, and they're really more than adequate typically for most mechanisms. Yeah, so I think we'll go on to the next one. So this gives a little bit of a picture on this noise issue or acoustic noise. This was a test done at a lab where they had a very large, the plan was to do a exported force and moment test in a clean room. And the clean room itself had a huge, optical bench. It must have been, I don't know, probably 12 feet by 6 feet, I don't know, 3 or 4 meters by a couple meters. And basically what we found was that the red curve there is really what the ambient noise conditions were in X, Y, and Z, for that environment when we turned off the primary air handler, although there were some other noise sources. At the same time, we used a granite block in a anechoic chamber, and recognized that there was quite a bit of improvement with the granite block. And in fact, we did some other testing, and that seemed to indicate that the optical bench actually appeared to be more sensitive to acoustics than the granite block. So it's one of these takeaways that the granite block might be the more general purpose tool to use as a platform. Certainly, anechoic chamber is also quite a benefit if you have that. But fundamentally, doing a noise or a background noise check is very critical. In this case, by the way, what was interesting, even though the anechoic chamber situation or setup was much better, the actual test didn't require that low of a noise floor, and it was more than adequate to do the test in the clean room with these conditions, where this black curve was actually a reference curve from another customer. That and it was in the vicinity of what could be achieved. So although you might be able to get the best noise, it might be that if for certain test articles it might not be required. So it's always good to understand your facility limitations and benefits, and it might be that more investment or more fine tuning needs to be done on the facility side to be able to achieve the lowest noise levels. In terms of mechanisms, I went through this on the part one, and certainly there's quite a few mechanisms that come into play. I'm going to touch upon a few different types of mechanisms to show you a little bit about that. First one was a reaction wheel. I mean, reaction wheels are pretty popular in that they provide attitude control, satellite attitude control, roll, pitch, and yaw, without the use of thrusters. And obviously, propellant on a satellite is a quite precious commodity. So these devices are quite sophisticated. They have a rotor, electric motor, and a rotor which spins. By as rotational speed is changed, it can change orientation of the spacecraft. And there's actually an attitude control system around this type of device, factoring in these parameters and then making the right commands to compensate. Well, with any reaction wheel, I mean, you're going to also, since it's a rotating mechanism, it itself has to be balanced, okay? And there's going to be an exported force and torque associated with that as well. So what I show here is just an example of what happens. I mean, when you don't have, say, a balanced reaction wheel or something ill-balanced, you might get a very poor pointing, where the pointing might span many pixels and really give you more or less a blurry image compared to what is really required is something a lot more stable. So characterizing the jitter or the AC component of a reaction wheel, because of its role in the orientation control of a spacecraft, is actually quite important to understand the overall capabilities or mission impact, if you will, on these exported forces and moments. And obviously, there's a balancing requirement too with these types of mechanisms. So, in terms of what this might look like, is you have a typical setup there is in the left-hand corner. And what researchers do in this field is look at static and dynamic imbalance. Okay, and what's done here is on the lower left-hand corner, what's typically done is a waterfall plot, where you would measure force versus rotational speed and temporal frequency, and you would do the same with moment, where the primary ridge would be due to the rotor itself, and then you would have these sub-ridges out in frequency, which be mainly due to, say, bearing vibration, for example. So in these types of measurements, characterizing the exported force and torque and understanding the quality of a balance, for example, really factor into what spacecraft designers want to see in terms of disturbances and how they might impact the mission itself. Then there's also another tool. In this case here, we used a dynamometer. And in this case here, this was a calculation where you calculated six components by virtue of those closed form expressions I showed earlier. In this case, this is about a 2.5-inch OD, or say 65 millimeter OD, and about a 4-inch height or 100 millimeter height force and torque link. So it does no calculation, and it's been used for sure for the smaller CubeSats to characterize the exported force and moment, much like what you saw in the full dynamometer test on the other slide. What's interesting about this approach is that you have 6 individual channels. Each are independent of each other and can be optimized independently. So it's quite a powerful tool when you have say a 6-channel amplifier. You can control each of the channels independently, giving say quite a bit of benefit in characterization. In this case here, we just did a quick test where the R&D engineer commanded a certain speed, and we were able to actually see it as a sine wave, as an imbalance, and be able to put cursors on it and figure out that we were absolutely viewing the rotational speed of the reaction wheel. So it's just one more example of a force and torque link to do the job as well, if the test article is small enough. Also, in these types of cases, I mean, when your reaction wheel is rotating at the lowest speeds, you also have the lowest disturbances, okay? So in one case, one of the user came up with the idea of using an optical tachometer to basically do coherent integration. And this is quite an innovative technique where you're actually just now integrating based upon a stable point as the wheel rotates. So this will definitely give you an improvement of signal to noise ratio, as shown below, where you might have a rather noisy looking signal at the lowest rotational speeds, but with coherent integration, you can definitely achieve a more deterministic view for sure. And in this case, 3 to 5, roughly reduced noise by a factor of 3 to 5 was achievable anyway. As far as satellite cryocoolers go, I mean, cryocoolers are devices which cool detectors, and they could be IR detectors, gamma ray detectors, X-ray imaging systems, and so forth. And there's various different technologies that are used in cryocoolers. There's a lot of technological expertise, with this technique, and a lot of evaluation going on for sure. So what's often of interest is really what are the harmonics, and how can they excite the spacecraft resonances, for example, and how does this impact the overall mission? So understanding the exported force and torque is absolutely critical. And in terms of both the the cryocooler, the pumps are usually the more the devices that make up let's say the largest parts of the exported force and torque for these characterizations of cryocoolers. But fundamentally, this could also in effect blur the image as well if not properly compensated. And there's a lot of compensation now going on with cryocoolers. There's a lot of active compensation where they look at ways of controlling the cryocooler so to mitigate any say high vibration. And there's quite a bit of passive vibration suppression, which we're going to talk about in a minute. This example here, by the way, is a project that's being worked at Utah State University Center for Space Engineering, and Dr. Swenson Anderson and Joel Mork are working this project. Anyway, we thought it would be interesting to show some preliminary data associated with this project, as well as, there's eventually be a paper processed or issued as well. If you're not familiar with Utah State, they also have a very prominent space dynamics lab there that's quite recognized in the space industry for sure. So what you see here is basically a diagram of a cryocooler, how heat comes in through the detector, and then how it's mitigated through the cryocooler and so forth. But we've got the cryocooler, which basically is a closed loop circulation of helium gas, to cool the cold finger. And then we have the thermal strap, which is in this case a PGS material, which provides high thermal conductivity as well as high flexibility. The optical detector itself can be, a variety of different technologies for sure. The wire rope isolators aren't shown in this schematic, but I'll point them out a little later. but basically they're passive cryo cooler mounts to reduce the exporter vibration. They're basically braided stainless steel devices. The heat exchanger, pump, rotating fluid joint, radiator panel are circulating Novak 7000 heat transfer fluid at about 75 psi or 5 bar, and that's a closed loop system as well. Obviously, we've noticed that the pump in this scenario really is also quite noisy. There actually is also a particle damper at the cold tip as well, where 300 micron stainless steel particles are used in a cavity or a reservoir. And the work that was done basically identified like a 50% fill was an effective way to mitigate some of the vibration for sure. And the radiator panel is motorized assembly, and it typically wants to be edge on to the sun to minimize heat loading. So here I'm going to just show a little bit more. Let me just see if I can put that up there. And what you see here is a 3-component force sensor that are coupled into the thermal strap right here. And then you have an accelerometer, 8763B, measuring the cold tip vibration. Then you have a dynamometer that you see underneath the whole mechanism. This is a 9139, measuring the exported force and torque of the entire assembly. This is an example of a particle damper. And this would be an example of where the vertical axis is, the displacer axis along the cold tip axis, and then the compressor axis that we'll refer to in the next slides. This is just say a more detailed view. I'm not going to go through each one, but basically this cryo cooler assembly is a part of a 6U CubeSat, an ATA called ATA, and so it's something to keep in mind. It makes up a large part of the 6U CubeSat. I don't know if you knew this as well, but Utah State actually hosts the Small Sat Conference every year, so they're very prominent in that field as well. So what I did was, instead of showing all the the detailed plots of each mechanism, what basically the plan of attack was to take each piece of the cryo cooler assembly and evaluate it separately, and then build up the rationale behind the final integrated assembly results. But what we showed here is basically that for the forces anyway, at the exported forces, there's actually two scenarios here: a loaded down case, which is where you don't have the wire rope isolators, and the red case is where you have a floating case where you have these wire rope isolators. And what we found here, certainly for forces and moments, that the wire rope isolators reduce the vibration by a huge amount. As you can see here, you almost have a 5 Newton in the compressor axis, and you're down to fractions of that by using the wire rope isolators. So passive isolation was viewed quite favorably in this evaluation. You can see here, these are the moments, and you saw basically a similar characterization with the wire rope isolators. What we did find that anyway was with the cryo cooler assembly and the cold tip, the wire rope isolators basically were found to have an amplification at lower frequencies. And one of the attributes of the cryo cooler is it did have a less than 100 hertz driving frequency. And as the wire rope isolators were amplifying some of that, we found that when the floating condition occurred, we actually resulted in higher amount of vibration than the lockdown condition. Obviously, the observation was that less than 100 hertz, you tend to get some amplification, and at higher than 100 hertz, you were getting more attenuation. So, continued work is ongoing, but this is definitely an area that would be for further improvement as well, with particle dampers and so forth. In terms of the exporter force at the thermal link, or where the detector would be, you can see here that, again, the wire rope isolators are at not only mounted underneath the cryo cooler assembly, but actually underneath the detector as well. And you see a definite advantage as well in terms of the reduction of vibration due to passive isolation. Next topic is going to be, in terms of pointing mechanisms with in terms of gimbal systems, antenna systems, the solar array positioning, and so forth. So the term stepper motors is often used in the industry, and they're quite high reliability devices and often used in a lot of the actuator systems. So what I wanted to do is just show a brief overview of say antenna systems, and these are just a couple different examples of antenna systems out there, space antenna systems. But basically, you would mount the entire antenna on the dynamometer and run an exported force and torque test using it in its operation at various positioning speeds, for example, where you would then measure the exported forces and moments. In this case here, what we found was that there were two actual modes of this gimbal system, and that was a normal mode or a slow positioning mode and a fast mode. And what we found was that by virtue of the stepper motors being used, that when they were being used in the fast mode, they were actually exciting the resonances of the structure itself of the antenna. Obviously, the antennas are being designed for low mass, so there's for sure compromises being made in terms of the structural design as well. So these types of inputs are invaluable to help characterize new designs, existing designs, and reasons for improvement if need be. So certainly positioning systems are definitely being evaluated in the same manner. What I wanted to do is just spend a few minutes on satellite release mechanisms and just say that the rules sort of change with transient events, largely because with a transient event, the frequency bandwidth is inversely proportional to the event duration. And depending on what type of event you have, if it's say a rectangular pulse event or a shaped pulse, a half sine pulse, you might have even higher demands in terms of frequency. So you could just take a basic Fourier transform of these basic waveforms and recognize that for anything rectangular in nature is going to have much higher energy out in frequency. Okay, and that could mean that you have to now, to be able to best represent that signal, you have to then now have more frequency in your force measurement system, for example, or higher frequency. So one of the takeaways for sure is there's an inverse proportionality. We did a test recently at one company recently where they had an optical shutter system, and looking at the specs of the optical shutter, it was a very low level torque that we were trying to measure and very fast. And I can tell you the dynamometer had to be optimized in terms of the mounting of the test article, certainly the mounting of the dynamometer to the table and so forth, and the resolution, and it was for sure there to be able to see the event in quite high fidelity. One thing I want to mention with transient events is that your force platform is very critical to get the highest natural frequency, because the bandwidth of your transient event needs to be separated in frequency from the natural frequency of the dynamometer. If it's not, you won't have any chance of filtering that out, and it'll be difficult to characterize the event because of that. So you definitely want to pay attention to transient events. They put an added demand on force measurement platforms, and for sure, if you have any questions, application specialists like myself can absolutely give some guidance in this regard. Okay. So now that we've gotten through mechanisms, I just want to touch a little bit upon force limited vibration testing. And I found this picture in a paper I read some time ago, and I thought it was quite an illustrative picture showing the life of a payload going out from launch to deployment. And you can see here in the illustration about the high levels of vibration at the initial launch periods, and you can see the transient levels of shock out when you're doing various, say, separation events and so forth. So quite interesting to sort of trace this through. So how do you deal with that? How is it being dealt with? Well, before I get into that, I just wanted to say there are some real life data as well. This slide basically talks to a GLASS mission which basically was instrumented to measure vibration and force, at launch and flight. And you were able to see that there were quite significant forces, certainly considerable levels of force, and for sure in some acceleration. I mean, you see here, in this case here at liftoff, you've got near almost 5,100 pounds of force at this frequency. And, that would be in metric system somewhere around, I don't know, what was it, 2,500 newtons would be probably an estimate. So quite substantial amounts of force. So how do you now test for that? Well, there's environmental testing that goes on, certainly with vibration testing of all sorts, and force limited vibration is certainly included. Shock testing, vibroacoustics, thermal vac chamber testing, and so forth. So there's a whole entire suite of tests that are normally performed on payloads. And the force limited vibration test fundamentally is that you want the force limiting solution to automatically notch the acceleration at the test item resonances, and what you're monitoring is the fixed base resonances at the interface between the shaker and the test article. And this is basically by notching these resonances, you're able to best replicate the test article mount in actual practice. The actual mount is somewhat compliant for the payload, so you do get some ability of not having these resonances excited by virtue of the launch conditions. So by replicating that, you actually help yourself not to over test the payload itself. So this is a technique that was developed back at I think JPL back in the 90s, and it's quite a bit used in the industry nowadays. And certainly as part of this, there's a extremal control system that is used to perform the real-time control, and setting up and controlling the shaker so that you get the automatic notching based upon the monitoring of the force and acceleration signals on the payload. And what you see here is just a simple example from this NASA report of what you would normally get if you didn't compensate for or have a notch due to the fixed base resonances. You would get quite a significant resonance exciting the structure. And indeed, what you want is you want to notch that out to get more of a level platform or level excitation. So this again fits into not over testing the payload, which is rather critical. This is an example back in NASA did this project back a few years ago, but I show it here just to illustrate some of the detail behind doing a force limited vibration test on a large observatory like this. Certainly quite substantial mass. Force ring also has some mass. Frequency response of the measurement isn't terribly high, but it is definitely 70 hertz is for this type of mass is quite substantial. 3-inch or 76 millimeter top and bottom plate made out of aluminum. Ring diameter is around 2.6 meters. 12 sensors were used, and custom diameter bolts, preload bolts, were used with Delron spacers to center the bolt into the force sensor. So this would be say a geometric example of what this would look like if you took the geometry of a 12 sensor system. You would come out with deviations from X and Y, these A, B, C, D, E, F factors. And this would basically give you a closed form set of expressions, which can be evaluated for forces and moments. And this is, in effect, would be how you would implement this. What I give here is just a basic example of what you might want to do in terms of just getting some rough estimates of allowable force and moments for a given platform in terms of the number of sensors. What sensors are you choosing? How much maximum shear force, axial force are allowable? How much bending moment? How much overturning moment could be allowable? And so forth. So it's just some rough calculations, obviously, just to get you in the ballpark of a fixture design. For sure, PE sensors are giving you the ability to range, And using the largest sensors are often done because they're also the stiffest sensors and give you the best frequency response as well. In terms of preload, I talked about preload last time. With preload, there's three main objectives there. You want to basically get linearity. You're preloading at 70% of the full scale range. Because the force sensors have a ceramic coating on top and bottom, there's roughly a 0.2 frictional coefficient, which basically means that any preload force is going to transmit to the shear forces by a factor of 0.2. So you basically have like a 5-to-1 ratio of preload force to shear force. And lastly, you want both compressive and tensile measurements to be done with a sufficient preload. So carry enough preload to not get slippage in the shear direction is actually rather critical as well. Oftentimes with calibration checkout, it's a dynamic in situ checkout. I went over this in part one. And in this case here, you would basically vibrate the test or the platform under the first resonance, maybe with a mass simulator, and you would then compare the apparent mass to the known mass, and that would give you an idea of what the calibration factors would be. Obviously, I talked about static checkout, but for these large types of setups, they're really not practical. But you can do a static checkout as well if you so chose on, say, smaller assemblies. It's certainly practical for small assemblies. Also, I mentioned before those closed form expressions. There's companies like M+P who have systems which can actually do real-time calculations for control. So they would take in every sensor output and be able to make these real-time calculations and control on vector notching or sum forces or overturning moment, for example. And a lot of times these types of systems are very prevalent out there, and they're very much used in terms of getting visibility on every sensor output, which sometimes is of interest, and having that real-time calculation happening is sometimes quite convenient. Also, what's done with controllers that aren't as sophisticated, and you would use, say, an analog processing method using, say, a Stanford research, sum difference amps and scaling amps, and you can basically build an analog network of signal conditioning that replicates these moment systems. Now, so these are definitely not as widely used, but certainly in cases where you don't have a controller with that capability of calculation, it's certainly an option if you need to do moment control. And in some cases, times there's a need to have a cross check against real-time calculations. So sometimes these analog systems are still used as a cross check. So I mention them just for completeness. And then lastly, I just want to go over a typical scenario here where you might have these 90 piezoelectric force sensors, and I introduced a lab amp, which is a dynamic charge amplifier, and in some cases this is being used nowadays to actually take the analog outputs directly into a controller, but because it's an integrated data acquisition system on top of a high fidelity charge amp, you're able to then get a backup data collection in the background with very little effort, and create your CSV file for the test that backs up the primary system, if that's of interest. Obviously, because these are dynamic amps, quasi-static amps are needed to preload, and those for sure would be used to be able to build up the platform. Now I'll go to just thrust testing. I got about 10 minutes left, and basically you've got both chemical propulsion and electrical space propulsion, where I'd say the electrical space propulsion is really advanced in the last years, and you see a lot of developments on the electrostatic side, electromagnetic and electrothermal type propulsion that are being used more and more. Certainly in terms of efficiency or specific impulse, the chemical rockets typically have a lower specific impulse but higher thrust. whereas the electric propulsion or ion propulsion, for example, would be a higher specific impulse with lower thrust. So there's definitely some options out there for propulsion systems nowadays. So for testing anyway, there's still quite a bit of testing being done with piezoelectric pressure sensors, piezoresistive pressure sensors, high temperature accelerometers, and a full spectrum of signal of sensors and signal conditioning, depending on the test. It could be thermocouples, it could be strain gauge sensors, and so forth. So there's still propulsion testing is more complex than just a thrust measurement. Okay, but in thrust measurement, you'll find strain gauge being used, and certainly piezoelectric force being used. And I mentioned before vacuum measurements; they're certainly applicable still. And I'm going to talk a little about thrust misalignment. As a question does come up, and there are some considerations to take on that. And certainly, whenever you have a propulsion test, you want to always make sure the thermal isolation of the force sensors is being taken care of, so not to get any transient excitation of the sensors with temperature, because that would result in, say, some unwanted errors. Just a strain gauge, basically. I mean, they're quite popular. I think there's a large population out in the test and measurement industry very comfortable with using strain gauge technology. Certainly, they're being used in pressure sensors, load cells, torque sensors, position sensors, and so forth. So, but basically, they're a mechanism or a sensor technology that relies upon a flexure to measure a change of resistance. And that change of resistance is directly proportional to the amount of load. So pretty straightforward. So on that basis, the question always comes up is, hey, what about strain gauge technology and piezoelectric? And I often find putting these types of comparisons together always a challenge, because it's hard to sometimes generalize, but I tried to take a shot at it here to give a perspective. Certainly, with strain gauge, I mean, they're very much optimized for static measurement, and they're very absolutely good with temperature compensation because of the way you can trim these resistive bridges. They've got very good accuracy typically, and quite widely used for sure. The piezoelectric sensor certainly is quasi-static in nature, so long-term, low-level thrust measurements are probably not ideal for that, but certainly high level, longer term thrust measurements certainly would be very much possible. Very stiff, high dynamic range. What's really a real plus in a lot of the applications I've talked about here is that you can basically take the initial load and tear it out of the measuring range solution. So if you have got a 1,000-pound, or I don't know, what is that? That's around 4 kilonewtons static load on your dynamometer. Sure, that's going to affect natural frequency, but you can tear that out and basically just optimize the measurement on the dynamic portion of the signal. So it gives you a better way to represent and to get resolution of those smaller level signals. Whereas strain gauges, of course, you have the static load and the dynamic one coupled in. So you have to make that compromise for sure in terms of the resolution. Again, it's just a way to give a perspective. I think in propulsion test, I still see a fair amount of strain gauge technology being used. So I often talk to people who are using piezoelectric sensors for thrust measurement and ask them, hey, what are the considerations you make for, why you use that over say strain gauge? And the feedback I get anyway is that certainly natural frequencies of the piezoelectrics are quite favorable. A lot of times the researchers were looking at results of, say, a strain gauge measurement, and they felt that there was a mechanical noise or, say, a mechanical filtering due to the frequency limits of, say a strain gauge device, where the piezoelectric had quite high bandwidth and was less susceptible to static loads of the test article, and they were able to see more fidelity in terms of short or fast acting events. Certainly, the other feedback I got is test stand adaptivity, because when budgets are tighter and tighter nowadays, it's they argued with me anyway that there's a common platform that can be ranged for various product lines that are being tested. So that offered an advantage as well. Certainly, calibrating test stands in this way, would also be one of the things that you'd want to do, and be able to calibrate for low level and high level. And this is certainly achievable with a piezoelectric solution. But fundamentally, the other feedback I got also was that piezoelectrics tended to be lower, much lower in inherent crosstalk, and because of that, really gave basically an overall cleaner data with piezoelectrics. So, although the industry is very familiar with strain gauge, I wanted to at least ask these experts, what are the aspects they look at to give you folks a feedback. Obviously, piezoelectric, is certainly an option with propulsion testing. One of the things I wanted to mention, because I've been out, looking at various installations with strain gauge. Certainly, there's in some applications dual redundant force sensors. You can certainly do that with piezoelectric and stack two sensors on top of each other. Certainly, in this case here, this is being done mainly for doubling the sensitivity. But you can certainly do a dual redundant approach. But shunt calibration, which is very famous for strain gauge type solutions, is not possible with a piezoelectric solution. Just a quick example of a custom dynamometer being used for a rocket engine test. And in this case here, there are also piezoresistive sensors as well as high temperature piezoelectric sensors measuring the combustion process. And certainly in this type of design, you can use these closed form expressions again to derive your 6 components, force and torque. One example I wanted to show quickly was really just refer to the NASA Orion project and SLS heavy lift. And certainly there's an interest for astronaut safety and having an abort capability where you have basically a rocket assembly which could get the astronauts away from the disaster and save lives. And that's absolutely an interest nowadays with these advanced systems. So what I wanted to show was just something on the NASA Orion attitude control motor, and what it has it has 8 gas, or it has a solid propellant gas generators with 8 proportional valves. They're equally spaced. 2 functions to basically act as a abort system to get the crew module away from the emergency and orient the capsule for parachute deployment. Underneath this platform is a dynamometer. Yeah, I just wanted to show that quickly. There's a dynamometer that basically is comprised of force links and measuring 6 components as well. So very much a dynamometer application, piezoelectric dynamometer application, where you can see this on a YouTube video. If you wanted to watch the entire video, it's up here. It'll be referenced. And one last topic I want to just mention is thrust misalignment. And this topic comes up from time to time, and it's a very sophisticated topic. I mean, it might be that you're interested in inherent alignment of rocket motors, or perhaps thrust vectoring applications. In some cases, there's a common dynamometer, a 9255C, which is basically a 10-inch by 10-inch dynamometer. What is that, about 250 millimeters by 250 millimeters? And basically it's sometimes a very interesting building block. But there's 2 basic approaches you can do to measure the alignment or thrust misalignment. One is to measure side forces, or X and Y forces, and the other is to measure moments. And by virtue of our simple calculations here, we reckon that the uncertainties are much lower with regard to measuring the side forces, largely because when you're measuring moments, the actual thrust application point, or FZ, might actually have some variation in it. And that variation in itself could cause moment factors which are far above the required moment to measure with say a half a meter type of moment arm. So we reckon anyway that doing a side force measurement is probably the more practical approach than measuring the moments at this point for this simple example. What we allocated was about a 30 Newton allocation for uncertainty in terms of the measurement of these side forces, where our estimated uncertainty was around 23 Newtons. And the factors that came into play was like crosstalk between Z and X and Y. For this case, we basically selected a dynamometer with low crosstalk. Linearity is also a factor in selecting a dynamometer with low crosstalk or low linearity or high linearity. That is quite easy to do. Certainly, the sensitivity of F, X, and Y, okay, is affected by this long moment arm here. So you have to basically do a calibration with a suitable fixture that can calibrate out what these XY forces are over, say, a half a meter lever arm. And we can get to that actually rather accurate, reduce the errors associated with that. Certainly the effect of crosstalk in the variation of the force application point, as well as the individual sensor sensitivity variation due to the FC force application point. So there's going to be variation. I mean, with the best estimates, there will be some variation, and that variation has to be accounted for in the error budget or uncertainty budget. Like I mentioned before, any thermal effects onto the dynamometer will have high errors. As you can see here, I mean, there's a substantial amount of, in the red curve, temperature variation. You can see that it has a prominent effect on the output. That doesn't mean that the actual, if you're in a steady state temperature environment, these dynamometers would exhibit a very stable performance for sure. But any sensor is going to have say probably an unknown response when it comes to a transient temperature. So you always try to protect sensors from transient temperature excitations if you can. Certainly flatness of the mounting, I've already mentioned that, and also making a very stiff coupling of the rocket motor to the dynamometer itself. So there's several factors that come into play, but as I mentioned before, the estimate came out to about 24 newtons with a 30 Newton budget. So it seems to be at least certainly achievable from this analysis here. So on that basis, we covered now mechanisms, we covered force limiting, we covered also propulsion systems, and showed a little bit about how these dynamometers can play a role in your measurement. Certainly, we covered quite a few topics from frequency response to vacuum operation, partial range, and installation, and so forth. So I'm not going to go through all that again, but certainly covered a lot of ground. And at that point, I did overrun by a few minutes. I apologize for that. But if there's any questions, I'd be happy to answer them at the moment.
Yes, thanks a lot, Bill, for this very nice and interesting presentation. We also got some very good questions in this session. So one was, if I use more than one sensor in between a plate and the plate is not perfectly manufactured, so it's not perfectly flat, is there a chance in overloading the sensor too much?
There's a chance of overloading, and there's also a chance, any uneven loading on a sensor can, if it's a substantial load, can actually even damage a sensor as well. So you want to take care on that. Where I've seen uneven or flatness and parallelism coming into play is also in frequency response. So what you'll find is that if you hold the tolerances that we talked about previously in terms of the load-bearing surfaces, you're able to achieve the best frequency response. I showed an example in part one, just putting a sheet of paper or a metal strip underneath a dynamometer, or a thin metal strip, reduced the natural frequency substantially. So I think probably more practically would be the frequency response as well would be adversely affected.
Yes. Another question is, what are the reasons to preload piezoelectric force sensors? So we already heard about linearity, but are there some other reasons
Yeah.
why?
Yeah, the three component force sensors are preloaded at 70%, for linearity, for shear force handling, because there's a surface coating on the force sensors that basically provide ground isolation, and provides a 0.2 frictional coefficient. So your shear force handling is basically 0.2 times the preload force. So by preloading at a high level, you're able to get very high shear force handling. And lastly, having the ability to do both compressive and tensile force handling, having, say, symmetric tensile and compressive force handling, is also one of the advantages to doing a preload.
Another question is, what is the use of the K factor? It seems like this value would change with applied loads and length of the lever arm. The spec sheet you showed us was given as a linear value.
Yeah, it does. It does vary. It would be a parametric evaluation with moment arms. Okay, so if your moment arm changes, you will see different factors. So that's for sure. And in some cases, it's requested. Okay, where there might be a common setup where the center of gravity is known, the lever arms are known, and then the calibration can be used. But you're right. I mean, if you change the geometries, the calibration changes as well.
Then last two questions. How should the calibration of a 6-component sensor be carried out? How to verify whether dynamic behavior is consistent?
This is a very good question. A 6-component. Now, I'm wondering if you're talking about say a dynamometer. I would assume a dynamometer. Well,
He
the way
was talking about the force and moment sensor. Yes, so 6-channel. Yeah.
Okay, so what's done, at least at Kistler, is there's an electric actuator system that applies a known force on the primary axis if you're measuring force or through a moment. And there's in line with the actuator is a piezoelectric load cell for calibration, as well as a strain gauge load cell, where the strain gauge load cell is being used to provide a feedback to the actuator, the electric actuator, in terms of the amount of force. And there's actually a force reference force sensor as well. So the calibration is really being done by a press, for a lack of a better term, and through either very precise force application points for forces, or through a moment or through a lever arm to derive moment calibration.
Thanks a lot. And now we are coming to the last question. When preloading a force sensor for a force limited vibration test, what is the best way to avoid any mechanical shorting of the gauge with the preloading bolt? Is it a simple bushing usually sufficient?
Yeah, I mentioned the Delron spacers that, at least in the example I showed, I think NASA was using. But yeah, you need a centering sleeve, for lack of a better term, a phenolic material that's a centering sleeve inside the OD or ID of the sensor. So you would put this centering sleeve in there that's non-conductive, and then you would feed the bolt through that. And this would basically align the bolt through the center, as well as provide the ability not to touch either the inside of that ID of the sensor to short the sensor up.
Okay, great. Thanks a lot for all this information. And as already told, so we will send the link to download the recording in the next few days. So you will have the chance to go through the slides and all the information from Bill again, if you missed some part. And it's my part to thank Bill a lot for this very interesting presentation, and keep safe and speak to you soon.
Yep.
Thanks a lot, everyone.
Take care.
Bye.
Bye.